Nearly 50 years after its launch, Voyager 1 is still traveling farther into space than any human-made object. Now scientists say it's approaching a remarkable milestone. The probe is nearing a distance where its signals take almost an entire day to reach Earth. Because of this extreme separation, researchers increasingly describe its location using light-time measurements rather than simple distance. This change reflects just how enormous interstellar space truly is. In this video, we will explore what Voyager 1's new distance milestone means, what scientists are learning from the spacecraft today, and what the future holds for humanity's most distant explorer. Let's get started. The recent attention around Voyager 1 centers on how far it has traveled and how scientists describe that distance. Voyager 1 was launched by NASA in September 1977. Its original goal was to explore the outer planets during a rare planetary alignment that allowed one spacecraft to visit multiple worlds using gravitational assists. During its early mission, Voyager 1 produced historic discoveries during flybys of Jupiter and Saturn, revealing new information about their atmospheres, rings, and moons. After completing these encounters, the spacecraft continued on a trajectory that would eventually carry it beyond the boundaries of the solar system. Today, the probe is more than 160 astronomical units from the Sun, traveling outward at roughly 17 kilometers per second. At this distance, Voyager is tens of billions of kilometers from Earth, making it the farthest human-made object ever built. For most of the mission, distances were expressed in kilometers or astronomical units. However, as Voyager moved farther away, scientists began relying more often on light-time measurements, which describe the time it takes for signals traveling at the speed of light to reach the spacecraft. This method is useful because communication with Voyager depends entirely on radio signals. Commands sent from Earth must travel across space before the spacecraft can respond, and the reply must then travel back to Earth. At the spacecraft's current distance, that round-trip communication delay can exceed 40 hours. The one-way signal delay alone is already approaching an entire day. Because of this, scientists increasingly describe Voyager's position using units such as light hours or light days. A light day represents the distance light travels in 24 hours, about 26 billion kilometers. Describing Voyager's location in terms of light time provides a clearer sense of scale. Rather than presenting enormous numbers of kilometers, the measurement directly reflects the physical reality of communication across space. When engineers send a command to Voyager, they must wait nearly a day to know whether the spacecraft received it. This milestone highlights how extraordinary the spacecraft's journey has become. What began as a mission to explore nearby planets has evolved into humanity's first long-term exploration of interstellar space. The significance of Voyager 1's journey goes far beyond the distance it has traveled. The spacecraft is now operating in an environment that had never been directly sampled before. In 2012, Voyager crossed a boundary known as the heliopause, the outer edge of the heliosphere. The heliosphere is a vast bubble formed by the solar wind, a stream of charged particles constantly flowing outward from the Sun. Inside this bubble, the solar wind dominates the local space environment. Beyond it lies the interstellar medium, the thin mixture of gas, plasma, and magnetic fields that fills the space between stars. Before Voyager reached this region, scientists could only study it indirectly using telescopes or theoretical models. The spacecraft's instruments provided the first direct measurements of this environment. One of Voyager's important discoveries involved the density of plasma in interstellar space. Using instruments that detect plasma wave oscillations, researchers determined that the surrounding medium appears denser than many earlier predictions suggested. This information helped refine models describing how the heliosphere interacts with the galaxy around it. Voyager also recorded a significant change in cosmic ray activity after leaving the heliosphere. Cosmic rays are high-energy particles produced by powerful events such as supernova explosions. Inside the heliosphere, many of these particles are deflected by the Sun's magnetic field. Beyond the heliopause, Voyager detected a noticeable increase in their intensity, confirming that the heliosphere acts as a protective shield around our solar system. Another unexpected observation involved magnetic fields. Scientists originally predicted that the magnetic field outside the heliosphere would differ dramatically from the field inside it. However, when Voyager crossed the boundary, the direction of the magnetic field changed much less than expected. This surprising result suggested that the interstellar magnetic field near our solar system may be more closely aligned with the solar magnetic field than scientists had predicted. Voyager's instruments continued to detect changes in plasma density and magnetic field strength as shock waves from solar activity propagate outward across interstellar space. Even though the spacecraft is now outside the heliosphere, powerful solar eruptions can still send disturbances that eventually reach it years later. By measuring these effects, Voyager helps scientists understand how the Sun interacts with the surrounding galaxy. More than a decade after entering interstellar space, it remains the only spacecraft capable of directly sampling this region. Although Voyager 1 continues to provide valuable data, the spacecraft is gradually approaching the end of its operational life. The probe is powered by radioisotope thermoelectric generators, which convert heat produced by the radioactive decay of plutonium into electricity. These generators allow spacecraft to operate far from the Sun, but their power output slowly decreases over time. To extend the mission as long as possible, engineers have been shutting down instruments one by one. Each shutdown reduces power consumption so that the remaining instruments can continue operating for several more years. Mission controllers must carefully decide which systems remain active based on their scientific value and energy requirements. This process allows Voyager to continue returning important data, even as its power supply declines. Maintaining communication with such a distant spacecraft also presents technical challenges. The signals Voyager transmits are extremely weak by the time they reach Earth. Detecting them requires some of the most sensitive radio antennas ever built. These antennas are part of NASA's Deep Space Network, a global system of communication facilities located in California, Spain, and Australia. The network allows engineers to maintain contact with spacecraft across the solar system and beyond. Another challenge involves keeping Voyager properly oriented in space. Its antenna must remain pointed toward Earth to transmit data effectively. In recent years, engineers successfully reactivated thrusters that had not been used for decades in order to maintain this alignment and extend the spacecraft's operational life. Looking ahead, Voyager may continue sending scientific data until the early 2030s. Eventually, its remaining power will become too low to operate any instruments, and communication with Earth will end. Even after that moment, however, the spacecraft's journey will not stop. Voyager will continue traveling through the Milky Way for millions of years, orbiting the galaxy along with our solar system. In about 40,000 years, it is expected to pass relatively close to another star system. Long after its instruments fall silent, the spacecraft will still be drifting through interstellar space. On board Voyager is a golden phonograph record containing images, sounds, music, and greetings from Earth. The record was designed as a message representing human civilization, intended for any intelligent beings that might someday encounter the spacecraft. Whether such a discovery ever happens remains uncertain, but the record serves as a symbolic reminder of humanity's desire to explore and communicate across the vast distances of space. Nearly 50 years after launch, Voyager 1 remains the most distant human-made object ever built. Its growing distance, now measured in light time, reveals the immense scale of the region between the stars. Even after its instruments fall silent, Voyager will continue drifting through the galaxy for millions of years.